Yeah, thank you very much, Stefano, and also a warm welcome from my side to all of you. So we are going to start with the thermodynamics related part, and Max will later on tell you more on how this will affect the future base medium speed engine. And we will start with the matrix of possible combustion systems that we are later on going to apply the alternative fuels to. So we've divided the matrix into, on the left side, the premixed Otto cycle combustion systems, and on the right side, the diffusive diesel-like combustion systems. So starting with the premixed ones, we have different ways of introducing the fuel. So we can, for example, use a central mixer, port fuel injection, or early direct injection. Early in this case, for example, for hydrogen would mean that we would start injection after closing of the intake valve. Regarding flame initiation, we also have different options. So we can use positive ignition, so a spark plug, unscavenged or scavenged pre-chamber. And then we would also have the option of using a pilot ignition, so a micropilot concept, as for example is used currently for natural gas. On the diffusive side, direct injection and compression ignition are mandatory, and for some of the alternative fuels, we will require some kind of ignition support. So the resulting combustion systems are a standard compression ignition combustion system, so for a diesel-like fuel, then a surface ignition concept where we have a fuel with a lower ignitability, but with a high tendency for hot surface ignition. And then we also have the dual direct injection compression ignition combustion system, which is a pilot diesel-assisted combustion system where we inject a small quantity of diesel to elevate the temperature level and subsequently lead to a fast ignitability of our alternative fuel, which has a lower ignitability just from the fuel side. And then in the middle between the premixed and the diffusive combustion systems, there would also be the option, which is shortly named here with DF. This is kind of a fuel sharing concept where we are using basically a base diesel engine and introducing an alternative fuel in the port. So for some applications, this might also be a valid option. So which kind of fuel do we see as most likely in the near future for these combustion systems? We are going to take a closer look on what is likely, but of course not on all the possibilities. So starting again with the premixed combustion systems, for hydrogen, we see a possibility, at least for the very smallest medium speed engines, and of course these are all, also operated with a higher speed, that we could realize a combustion system with an open combustion chamber and a spark plug. However, for the natural gas-like fuels, and also for methanol, this might be an option. We will most likely use a scavenged pre-chamber layout, and also for hydrogen, for the larger medium speed engines, this is the most likely option, as hydrogen has a very fast flame speed, but it's of course not infinite. The micropilot concept is, of course, widely used in the dual fuel marine engines with natural gas, so natural gas and SNG, so methane basically, or also maybe biogas in some amount, are likely options for such a combustion system, and also for hydrogen, this could be a good option. However, here we have to keep in mind that we need to lower the compression ratio in comparison to natural gas, and therefore we have to be careful with the micropilot ignition. The named DF or fuel sharing concept might be an option for hydrogen. So usually with this kind of concept where we have a very lean background mixture, we have very high HC and CO emissions. But for hydrogen, obviously we don't have this problem, and therefore it might be an option also to have a fast ramp up of a hydrogen engine in the portfolio. Moving on to the diffusive side, so for the standard compression ignition combustion, synthetic diesel or Fischer-Tropsch fuels are an obvious candidate. For such a combustion system, also what Benedict has talked about, so DME could be used. However, we would require some kind of adaptation of the fuel system for that, of course. And then what we also see very likely on the diffusive side are methanol and ammonia with a pilot-assisted diffusive combustion system. And we are in this session going to focus on hydrogen on the positive ignition side mostly, and then also we will start actually with a section on methanol and ammonia for a diffusive combustion system. For this purpose, we are actually starting a little bit with the fuel properties. So starting from the fuel itself, as especially ammonia is still quite unconventional as a fuel. So Benedict has shown that there are already applications, of course. So, for example, in the war, there was a bus operated on ammonia, and there are some pilot projects. However, I think for most it's still quite unconventional as a fuel. So, starting with the lower heating value, we can see here both for methanol and ammonia, we have a heating value which is roughly only half of that for diesel or MGO. But this lower heating value does not result in a lower energy content in the cylinder. So we can see the mixture heating value is even increasing slightly. The main effect is to be seen here for the fuel tank size or for the fuel volume that we need for a certain energy content. So the storage is not included in these figures here. So for methanol, we would need to increase the fuel volume by 130%, and for ammonia, this would be 180%. Still, for ammonia, the storage density is its major advantage compared to, for example, hydrogen, or especially hydrogen. So the additional space that we require is only about 50% of that for hydrogen, and also the temperature for liquefaction at ambient pressure is only minus 33 degrees compared to hydrogen, where we have minus 253 degrees. So therefore, we will also require less insulation or less energy for reliquefaction of the fuel. So moving on to the little bit more combustion-related properties, we can see here both for methanol and ammonia, we have a lower adiabatic flame temperature, which would be beneficial for our NOx emissions. However, for ammonia, we have to consider here that we are burning a fuel that has nitrogen on board, basically. So we are producing nitrogen radicals, which will be worsening our NOx emissions quite severely. And then the ignition temperature and flammability limits, we can see ignition temperature is higher for ammonia and flammability limits are very narrow. So there will be major challenges regarding combustion. And we are going to have a closer look on this on the following slide. So for that purpose, we have depicted here ignition delay times and flame speeds. And we are starting with the ignition delay times. So in dark blue, we have depicted here methanol. In the light blue, it's methane, so as a reference for natural gas, so for a quite knock-resistant fuel. In gray, we have ammonia. And in red, we have dimethyl ether as a reference for a diesel-like fuel. So if we look at methanol, we can see with a little bit of pilot support, so a little bit elevation of the temperature level, we are already getting close to diesel-like ignitability. So therefore, this is quite a good option for such a diffusive combustion concept. Looking at ammonia, however, we can see the ignition delay times are even longer than they are for methane. So therefore, we will require a lot more pilot fuel or a higher compression ratio or a combination of both. And looking at the flame speeds, we can also see in comparison to methanol or methane, the flame speeds for ammonia are about 6 times lower. So therefore, we will also have to make sure that we have, during our diffusive combustion, a quite high temperature level to ensure a full and complete combustion of ammonia, as from the fuel side itself, it does not really want to burn that well. So coming from the fuel properties, we can now have a closer look on the diffusive combustion system that we are actually aiming for with these two fuels. So as the pilot-assisted combustion system may be unfamiliar to many people, we've depicted it here in 3 phases. So we are starting with the pilot injection. The pilot injection is from this first picture to the second one being compressed to ignite. Then we have the pilot combustion in the second picture. And we can also start the main injection of our fuel, so ammonia or methanol. And this main fuel is then compressed to ignite, supported by the elevated temperature that we are creating with our pilot diesel injection. And then subsequently it's compressed to ignite and has a main combustion phase and burnout, of course. So really operating like a true diffusive combustion system, but with basically 2 direct injections and also 2 compression ignitions. So what can we say already on this combustion system, just coming from the fuel properties? So we've seen this on the ignition delay time. So the pilot quantity for methanol will be much lower than it is for ammonia, and for methanol we had a quite comparable ignitability with a little bit of support compared to the diesel-like fuels. So therefore we can mostly take over the combustion chamber here and also the compression ratio, while for ammonia it's likely to be a little bit higher. What is basically the outcome of this regarding performance and emissions? So we have a short overview here of this. The baseline is the MGO or diesel, basically. So as with methanol, we have the same compression ratio. We can realize basically a similar load range with similar efficiency. We have a severe reduction of the NOx emissions due to the lower adiabatic flame temperature, but also due to evaporative cooling of methanol. And then the rest of the emissions are basically very low as we have a diffusive combustion system. For ammonia, on the other hand, we require a higher diesel share and maybe a combination of a higher diesel share with a higher compression ratio. So load range will be somewhat limited. And also efficiency is suffering a little bit from the early pilot injection. So this is thermodynamically, of course, not really ideal. NOx emissions are increasing as we have free nitrogen, although the combustion temperatures are lower. But the major advantage of ammonia, obviously, is that we are inherently CO2 free. So CO2 emissions are only produced from the pilot injection. So we are going to have a little bit closer look on this combustion system with a few results from our testing on single-cylinder engines with methanol, and we are going to discuss a little bit what this could look like for ammonia as well. So we are starting with a plot of the rotational speed over the bore diameter. So this type of combustion system is maybe familiar to you from MAN's MELGI low-speed engines or from Wärtsilä's gas diesel engines, which are operating with a similar principle. And we have, with our single-cylinder investigation, scaled this combustion system to heavy-duty and high-speed engines. The major challenge for such a combustion system, as we have two fuels and two compression ignitions, is of course the time frame that we have for our combustion. So therefore, higher engine speeds are really a challenge, and we have scaled this to these smaller engines, but we feel confident to apply it also to at least the smaller medium speed engines. So looking at results, we've selected to show here something on the heavy duty single cylinder engine. Of course, the size is much smaller than for the medium speed engines, but as mentioned before, it's really a diffusive combustion system, and therefore scaling regarding the engine size is not that much of an issue. So starting with the results here, as mentioned, these results are on methanol, but we also have a direct comparison to a diesel baseline. So we can see here at first, even with EGR that we are operating the engine with for the heavy duty, we have a completely soot-free combustion. So this might also be interesting for medium speed engines, especially with two-stage turbocharging, as we don't have to worry about soot impacting the compressor wheel. So this might also be an enabler for EGR combustion system for some medium speed engines. Then regarding HC and CO emissions, we can see we have a very low level apart from the very low NOx emissions where we have a lack of oxygen basically. So we have really a true diffusive combustion system, and at the same time we can increase the efficiency with this type of combustion system by about 5%, while NOx emissions for methanol are reduced by about 60%. So considering the properties of ammonia's compression ratio in the range of 18 might be really the borderline of what we can really go for, and we have to increase the pilot quantities. So therefore, efficiencies will most likely go down to the level that we see from the diesel engine, or maybe a little bit lower. But there will of course be ways to further improve this once we are really getting into this. So now we've focused quite a lot on methanol and ammonia, and it's time to move on now to hydrogen. So we've said in the beginning that we want to focus also on hydrogen, and for that purpose we are actually going back to the matrix that we've shown initially and are going through the combustion systems in a little bit more detail. So as stated in the beginning, for the hydrogen internal combustion engines, we see the possibility for the smaller medium speed engines to also go for an open combustion chamber, as we have a much higher flame speed compared to natural gas. So this is basically shifting the limit for an open combustion chamber, of course. But flame speed is not infinite, so therefore pre-chambers will also have their place for the hydrogen internal combustion engine. So for natural gas, usually a limit is somewhere in the range of 170 millimeter. For hydrogen, we think it could be somewhere in the range of 250 millimeter. For some applications, maybe a little bit smaller. For others, maybe a little bit larger bore diameters. What do we have to think about additionally for this scavenged pre-chamber layout? So the scavenging is also a challenge for methanol. For hydrogen, as for natural gas, we are using usually just the fuel to flush the pre-chamber. But for hydrogen, this will be very critical, especially regarding self-ignition. Then the micropilot concept might be a very good option also for hydrogen, as it is already a very good option for natural gas. And we can realize a fuel redundancy with a second main diesel injector, which is of course beneficial, for example, for the marine applications. However, for the micropilot concept, we have to think about the compression ratio, as if we need to go down for hydrogen to avoid knocking combustion with the compression ratio, we have to be careful that we still can realize a good ignition quality of the micropilot. Then the DF or fuel sharing concept, we've mentioned that in the beginning, this might be an option for the hydrogen combustion engine, as we don't have the issue that is associated with such a type of combustion system with HC and CO emissions. But this is, of course, just then the entry to the hydrogen internal combustion engines. Regarding diffusive combustion, we don't see this at this point as very likely for hydrogen, as we require a high injection pressure, so above 300 or 400 bar. So therefore, we would require a compressor or a cryogenic pump to really realize this with hydrogen, and we think it will be more in the direction of positive ignition or micropilot ignition for that reason. On the positive ignition side, we are going to have a short look with some of the results from our heavy duty and medium duty engine testing. Of course, much smaller, and scaling is not as easy as for the diffusive combustion system. But this slide is really summarizing the main challenges that we have with the hydrogen internal combustion engine. So on the left side, we have heavy duty results, which are comparing direct injection and port fuel injection. So we can see we have a really severe reduction of the boost pressure demand for the direct injection. So this is why hydrogen engines will most likely go for direct injection, at least in the longer term, as we really have a lot to gain regarding the boost demand here. However, this comes with a downside. So we can see here on the NOx emissions and also on the efficiency, the NOx emissions are much higher and efficiency is lower for this operation strategy. So we have operated with a boost pressure equal to the back pressure. So therefore, the mixing is really suffering with the direct injection, as we are having a low pressure direct injection. So in this case, around about 15 bar. And mixture formation optimization is the key to basically meet the full potential for the direct injection, that we not only have the benefits regarding the turbocharging or the boosting, but also that we are meeting the PFI layout, and that we can then translate the benefit regarding boosting also in higher efficiencies. And then on the right side, we have the medium duty results, which are showing the severe challenge that the load range is posing for the hydrogen internal combustion engine. So we can see with this two-stage turbocharger, we are enriching with increasing load, as we just cannot cope with the boost demand. Also for the higher loads, the result is increasing NOx emissions. And also we have to think in the higher load range about pre-ignitions and also knock. And to really get the best trade-off for the load range and also for transient capability, it's really important to also optimize the compression ratio. So in comparison to a natural gas baseline, to maybe reduce it a little bit to have a little bit more room regarding knocking combustion. For that purpose, we utilize a comprehensive toolchain from 0D to 3D that we've also validated with our test results. So we are starting 0D with a kinetic entrainment model to optimize the compression ratio. Then on the 1D side, we have valve timing optimization and turbocharger optimization on a full engine, of course. And then of major interest, and which we are going to focus a little bit more on the next two slides, the 3D CFD mixing simulations, which is for the direct injection especially of major importance. But we also do 3D kinetic simulations, so combustion simulations, which can also serve then as an interface to engine mechanics and so on. So as mentioned, focusing on the mixture formation, this will actually be the last part of my presentation, and then I will give it over to Max. We are seeing here three different cases for the hydrogen direct injection engine. So central direct injection. So this might be a valid option for the smaller medium speed engines where we are igniting the mixture with a spark plug, where we could be able to place a spark plug and injector in the central position, and then two side injection cases. So for pre-chamber layouts, for example, it will be very challenging to fit both a pre-chamber as well as a hydrogen direct injector in the middle. In this case of the side injection, one time we have it without swirl and one time with a swirl number of 1.5. So starting with the central injection case, we have, of course, a quite uniform distribution around the center axis. And if we consider that we might be able to ignite the mixture also in the middle with a spark plug, this could be a beneficial solution. For the side injection cases, we have severe challenges for the mixing. And we can see also the charge motion, so swirl is not having a major impact on this. So therefore, the optimization of the spray formation, of the spray targeting, but also of the interaction with the piston. So we can see we use the piston to redirect spray here, is really, really important. These are, of course, not the optimized solutions, but just examples. So there is, of course, a lot of potential that we can utilize with further optimization. And finally, having also a look at the mixture formation at the spark timing, we can see here in the central case, we have in the compact bowl of the heavy duty engine a richer concentration, which is beneficial for a fast combustion speed, while we have a major stratification in both the side injection cases, which would then result in a slower combustion, but also in higher NOx emissions, as somewhere we will also have quite rich spots. So therefore, it's really very important for a hydrogen direct injection engine to utilize the full potential. And for that purpose, it's very important to have a validated spray model to, for example, as shown on the right side, also be able to predict the interaction of the injection with the charge motion and so on very well. So this is sadly already the end of my part of the presentation. Max will now take over and give you more insight on the base engine topics. So I want to thank you very much for your kind attention. And of course, after Max's presentation, I'm also open for your questions. So Max, please take over now.
Yeah, many thanks, Arne, for that compact overview of the thermodynamic background. Now we come to the translation of this thermodynamics to engine hardware. As we can here see, methanol and ammonia can be generally seen in their behavior and requirements comparable to diesel. Especially ammonia needs even higher compression ratio and peak firing pressure capability. Hydrogen and natural gas benefit from higher boosting. For hydrogen, we see a spark-ignited combustion with a lower pressure for direct injection. For the diesel-like combustion systems for methanol and ammonia, SCR still will be needed. For hydrogen and natural gas, it will depend on the legislation to be applied if and which EITS will be needed. So to step in a more concrete detail, I would like now to show how existing dual fuel engines using natural gas and diesel as fuels are already a very good basis to burn hydrogen also. What is therefore needed is shown here on the right side. So as you can see, the example is taken from a normal dual fuel engine, and what now should be changed if we want to run on hydrogen is the compression ratio, because we have a higher knocking tendency. Also, the induction system with hydrogen adapted valves and a hydrogen adapted fuel supply. So the SOGAF needs adaptation for lower volumetric heating value. And of course, also the turbocharger for the increased boost pressure demand due to the lower volumetric heating value of the hydrogen. On what also has to be considered is that hydrogen operation is with even leaner lambda values, leaner fuel ratios possible. Of course, we have to also consider safety measures for hydrogen. So double wall piping for marine application, is this already usual, has to be considered, crankcase venting, and also hydrogen detectors. From today's perspective, future engines should be able to run on different kinds of conventional and alternative fuels, as we can see on that matrix here. It will be beneficial if engine architecture in general, and cylinder head architecture in particular, will be able to cope with that in an efficient and modular way. As we can see here, we see methanol and ammonia with diffusive combustion will have a setup very similar to diesel engines. When we come more to the alternative fuels, burning hydrogen, we see that it will be also come to scavenged pre-chambers, especially on bigger bore size, comparable to natural gas burning. And we see also premixed burning system, combustion systems for methanol and also with scavenged pre-chambers. So to show this better, we have here different mock-ups of important elements to be implemented into the cylinder head and which are needed to operate on different kind of fuels. So we start here with normal diesel system mock-up, which is relatively lean and easy compared to this what will be necessary to run on other fuels. On the right side, we see the dual fuel mock-up, where we have already added a pilot diesel injector and where we also have a gas admission valve to get the gas into the intake channels, intake ports. Then now we come to this diffusive methanol and ammonia combustion systems, where we can run with this setup of a central main injector for our alternative fuel, and where we need the diesel pilot injector to ignite the combustion. Premixed methanol running on a scavenged pre-chamber is then shown on the right side, where also we see that we will have in-cylinder pressure sensors as an feature necessary for the serial application of that engines, because we will need a closed loop combustion control. And as we also can see here, the methanol injector is placed also here in the side to inject the methanol into the intake channels. Now we come to this premixed hydrogen direct injection. So we see here that additionally we have to place now the direct injector also somewhere in the cylinder head. for the H2. Still, we have the scavenged pre-chamber. And on the right side, we see the alternative for that to run with a gas admission valve on the intake system. But as we see or saw before, for larger engines, we think that we have to run on direct injection. So, as we already mentioned several times, direct injection of that alternative fuels will play a significant role. In this slide here, we want to show how the combustion of methanol, ammonia, and hydrogen, and also the effects of burning that fuels, will differ compared to diesel combustion. On the lower part of the table, we point out also the challenges which we will face by operating that fuels. So as we can see here, compared to diesel, for example, methanol will have an decreased lubricity. It will have an increased corrosivity, and also it will have a higher tendency for cavitation. Similar tendencies, but even stronger, are expected for ammonia. And concerning the lubricity, we have this also for hydrogen. And for hydrogen, we also see that embrittlement will be a topic. As challenges or as general tendencies, we see that because of these challenges described here, with needle impact, cavitation in the nozzle, pressurized leakage, we will have reduced injection pressures, and so we expect that we will see injection pressures here in a range of 700 to 1000 bar, depending also a little bit on the fuel. Also, here on the lower table line, we see that also cavitation in the control valves, corrosivity will be a topic, and in general, when it comes to hydrogen, the topic of the storage, the cryogenic pumping, which is necessary, and maybe a high pressure compressor will be a challenge. So on this slide now, that we see that variability in the valve train is something what maybe can support also this kind of combustion systems, but we do not see it as a mandatory thing. So due to this different combustion behavior and combustion properties of these alternative fuels, it can be that in some let me say minor perspective, and for example, variable valve training could have some beneficial effects, but in general, it should be possible that we run with normal, constant valve timing. One of the reasons for that is that these combustion systems can work with reduced valve overlap, or does this even require and do not need this variability for larger and smaller valve overlap. So a very important point in every new engine layout are the requirements for the boosting system. These requirements are generally related to the chosen combustion system and the combustion system behavior of the fuel burned, which is also influencing the achievable BMEPs. So what we show here is that, especially as you can see on the hydrogen, even we have an increased BMEP level decreased BMEP level by burning hydrogen compared to a diesel operation, we have an increased boost demand. So the red bar is always the comparison to the basis from a diesel engine, and we see then on the black on this aquamarine blue bars how this the BMEP and also the requirement for the boost pressures behaves relatively to that. As we can see here for ammonia, we will see lower levels which are fitting to each other, lower BMEP levels, also lower requirements on the boosting. Like I already said, for hydrogen, we see more and higher demand on the boosting system. Therefore, we have here some slides to show the possibilities for different ways to arrange a two-stage turbocharging boosting system. We think that these two-stage turbocharging systems will play also a significant role in the future for medium-speed engines, maybe increasing role, and especially when it comes to the combustion of hydrogen, as we saw before, they are very helpful. I do not want to step too much in detail. I just want to explain that there are some advantages or disadvantages depending on that how you arrange the low pressure and high pressure turbochargers. What is of course clear, and also some alternative ways are possible to arrange low pressure and high pressure turbochargers on both sides of the engine, on free-end side and coupling side, and of course also the possibility to arrange a separate unit away from the engine and to come out of vibration issues and other negative effects. Another important topic or important thing we saw also from the slides before is of course the possibility to have a variable compression ratio. And therefore I want to show here FEV's possibility to make a connecting rod with the capability to adjust during the operation the effective connecting rod length. This is done in a way that we have here an eccentric piston pin bush, which can be adjusted by a switchable valve in the on the big end of the connecting rod, and by this, with some switching some different oil flows, this eccentric piston pin bush can move in a certain angle, and therefore, and combined with this eccentricity, we can change the effective connecting rod length. So in these diagrams here, you can see the effect of such an VCR system when you run a dual fuel engine in diesel mode, like we see here on the left side, and you have a not optimum compression ratio for the diesel operation. You gain disadvantages in the efficiency, and by switching the compression ratio to a higher value, what we can see here in that graph on the right side, where we switch from 12.3 to 17 on that path of the red line, where we are changing the effective length of the connecting rod by 14.2 millimeters. We can adjust this compression ratio and increase the efficiency in the diesel mode. And same things can be done when we operate now on alternative fuels. For example, operation on methanol, depending on the load point, it can be beneficial to have, for example, here a reasonable bandwidth of 16 to 19. What can be realized with a certain eccentricity. And also when we run, or see here the example for running on ammonia, and we can switch from 19 to 23. The development of this VCR system already, some of the quality gates are already taken, and we are at the moment in the mechanical component testing. So, and of course, a lot of CAE detailed design and things are already done successfully. So now one of the last slides I want to present to you and to show are the general correlations we see with additional pollutants where we have to deal with when we run on alternative fuels. So, for example, again, the comparison to the diesel and to the natural gas operation, when we are looking here on that column running on hydrogen, so we see that particulate numbers will become a topic coming from the oil, which is still in a very small amount, also a part of the combustion, unfortunately. And what we also can see here is which EATS system will we need. Depending on the regulation we have to deal with, it can be in the case of hydrogen that we will not need any EATS, or we can use a typical SCR system. For methanol, we have much more things to consider. So we can have coal monoxide, can have HC emissions. Also formaldehyde can be a problem, NOx as well, and also again the particulate numbers. So therefore, we see that SCR systems, urea-based, can be or will be needed, and also oxycuts maybe. Running on ammonia, we will also face ammonia slip as one of the pollutants, NOx as well, due to the high compression ratio, and again the particulate number from pilot injection and oil. Here is again mentioned that the urea SCR is a means to reduce the NOx, but of course they can be also considered that NH3 by itself it has reduction potential and can be used more or less with the same catalyst. Another slide also with respect to these SCR systems shall show that it can be beneficial also to introduce an high pressure SCR, which we can see here on the right side. Normally we are used at the moment to use low pressure SCRs after turbine. And of course, what can be considered is to think about the implementation of high pressure SCRs, which of course then offer some huge advantages. We work on higher pressures. We can reduce the volume, the required volume of that system, and also the temperatures are on a higher level, on a better level. And so in the end, we can come to more effective, efficient and effective SCR systems, also with respect to requirement of space. One of the last things I want to mention in my speech here is the possibility to test catalysts, especially also, like it is stated here, the aging of catalysts coming from the oil particles. And therefore, we have a special test bed where we can put in oil particles into this gas stream, exhaust gas stream, and can test the behavior of these catalysts or the reaction of these catalysts when these negative things are impacting them. One last thing is condition-based monitoring. which will become also a more interesting topic as well in the future of these engines. FEV is preparing condition-based monitoring systems and the logics and so on already since some time, and yeah, I should now be ready with my speech. Yeah, so sorry for this. I'm now already through with this, and I think altogether with this package, I think we will see a future of very modular, high efficient, connected, defossilized, medium speed engines. And yeah, I wish all of you and also for us at FEV that this future will take very long time still from nowadays. Many thanks, and now I will be open for your questions.